While the world was watching Japan on Tuesday, a fault most Californians have never heard of moved for the second time in 5 weeks. The United States Geological Survey logged more than 160 events in the sequence within hours and flagged the earthquake as a potential mainshock. That word, potential, carries the entire uncertainty of the science. This fault runs straight toward the Bay Area, and its buried record holds ruptures larger than anything in the modern catalog. Here is what it has done before, and the one signal that tells us what comes next. At 7:40 and 6 seconds on Tuesday evening, Pacific Daylight Time, the ground 5 miles east-southeast of Cloverdale, California, broke. The United States Geological Survey put the magnitude at 4.3, revised upward from an initial 4.2 within the hour. The depth was 5.5 kilometers, roughly 3.5 miles, which in earthquake terms is almost at the surface. The Northern California Seismic Network catalog lists it slightly deeper, at about 6 kilometers. Either number places the rupture inside the shallow, brittle upper crust, the layer where the shaking is felt hardest for the energy released. Nobody was hurt, no buildings came down. The survey's automated impact system issued a green alert for both fatalities and economic loss, the lowest category the scale has. More than 520 people filed felt reports, from Healdsburg, Geyserville, Middletown, and Kelseyville close in, and from Roseville, Elk Grove, and San Francisco, more than 100 kilometers away. The strongest recorded shaking reached intensity 5 on the modified Mercalli scale. That is, dishes rattling and pictures going crooked, not structural damage. A magnitude, 4.3 in Northern California, on an ordinary week, is a local news item. It gets a paragraph, a map, graphic, and it disappears. This one is different for 3 specific reasons, none of which have anything to do with how hard it shook. The first reason showed up in the survey's own product feed within hours of the rupture, and it is the number that should have made this a national story. The agency did not classify the Cloverdale earthquake as an isolated event. It classified it as the potential main shock of an earthquake sequence. More than 160 seismic events were associated with that sequence in the hours following the initial rupture. That is the figure the survey's earthquake sequence product returned, and it is the single most important number in this story. Here is why it matters. Aftershock productivity scales with main shock size. And the expected population for a magnitude 4.3 is a handful of small events, maybe a dozen, decaying quickly and quietly. A sequence population in the hundreds is not that. It is high productivity, and high productivity means something specific about the rock. When a single locked patch on a fault fails cleanly and then settles, you get a small aftershock population. When a broad volume of crust is sitting close to failure and one piece of it lets go, the stress redistribution lights up everything around it. That is what 160 events looks like. It is not one patch breaking. It is a section of the Earth's crust actively reorganizing itself. The survey's forecast product added a specific expectation, at least one aftershock of magnitude 3 or greater within the following week. That window opened Tuesday night, and roughly 5 days of it remain. None of that would matter if the earthquake had happened somewhere anonymous. It didn't. And that brings us to the second reason. The Cloverdale epicenter sits on the Maacama fault system, and almost nobody outside of working seismology has heard of it. The Maacama is a right lateral strike-slip fault running northwest to southeast through the Northern California coast ranges, east of the San Andreas. It dips somewhere between 50 and 70 degrees to the east. It carries a substantial share of the motion between the Pacific and North American plates through this part of the state, motion that has to go somewhere, and that the San Andreas by itself does not absorb. Its slip rate is about 9 millimeters a year, plus or minus 1.5, according to the deformation model built for the 2023 National Seismic Hazard Model. For comparison, the San Andreas offshore of this same region runs at roughly 24 millimeters a year, the highest rate on the local map, and yet has produced almost no cataloged earthquakes along that section. The Maacama also creeps. Creep is slow, continuous, aseismic movement. The blocks on either side sliding past each other without producing an earthquake at all. On the Maacama, that rate is somewhere between 2 and 6 millimeters a year. You can see it in the built environment, curbs and infrastructure crossing. The fault trace have been measurably offset sideways. Creep gets described in public as a pressure release valve, and that framing is where the reassurance comes from. It is badly incomplete. The researchers who documented this fault's recent behavior put it directly. While creep does bleed off some potential seismic energy, there is still seismic strain accumulating along this fault, which we can expect to be released in earthquakes. Run the arithmetic. If the fault moves 9 millimeters a year and creep accounts for 2 to 6 of them, then somewhere between 3 and 7 millimeters a year is not being released aseismically. That residual accumulates as elastic strain in the rock. It does not disappear, it waits. The third reason this earthquake matters is that it was not the first one. On the morning of June 24th of this year, at 10 minutes past 8 local time, a magnitude 5.6 struck near Ukiah in Mendocino County. The epicenter was directly beneath a Buddhist monastery in a sparsely populated stretch of mountainous forest. It was the largest earthquake in that region in nearly 9 decades, and, more to the point, the largest earthquake ever attributed to the Maacama fault in the survey's entire catalog. The shaking was severe close in. Seismometers within 10 kilometers of the rupture recorded intensities between 6 and 8. The survey's impact model estimated about 10,000 people experienced intensity 7 shaking. More than 4,500 felt reports were filed. Thousands of Mendocino County residents lost power. There was minor damage and there were injuries. The focal mechanism matched the Maacama exactly. One nodal plane oriented northwest to southeast, dipping 54 degrees to the northeast, consistent with both the local seismicity seen in cross-section and the fault geometry established independently in the published mapping. So here is where that leaves us. The Maacama fault produced the largest earthquake ever recorded on it on June 24th. 34 days later, it produced a magnitude 4.3 with a sequence of more than 160 events, 55 kilometers to the south-southeast, along the same structural trend. 2 notable earthquakes, 5 weeks apart, on a fault that had never before produced a catalogued event above magnitude 5.6 in the entire instrumental record. That does not mean a large earthquake is coming. The instrumental catalog is short, and short catalogs generate apparent regime changes that turn out to be artifacts of sampling. What it does mean is that a fault the public has never heard of has now twice demonstrated that it is doing something. The June 24th earthquake taught a second lesson, and this one is uncomfortable. Shake alert, the earthquake early warning system covering the West Coast, the most advanced public system of its kind in the Western Hemisphere, worked. It detected the rupture. It issued an alert. Roughly 657,000 warnings went out through the MyShake app, and the people in the zone of strongest shaking got the alert after the strongest shaking had already reached them. The first Shake Alert message went out 5.5 seconds after the earthquake began. In 5.5 seconds, seismic energy has already traveled outward roughly 18 kilometers. Everyone inside that radius was already being shaken when the alert was generated. Then add transmission time, cell networks, app delivery, the phone in your pocket, and that blind radius expands further. The researchers who documented it stated the conclusion plainly. These systems are not predictors, but rather detectors. They will never provide timely warnings to epicentral areas. That is not a criticism of Shake Alert. It is a description of physics. An earthquake has to start before anything can detect that it started. The warning travels at the speed of light, and the damaging waves travel at a few kilometers per second. So the further you are from the rupture, the more warning you get. 30 seconds in San Francisco for a distant quake is genuinely life-saving. But directly above the fault, the math cannot be beaten. The public conception of early warning as a form of prediction is simply wrong, and June 24th is the clean documented case that proves it. 5.5 seconds to first alert, 18 kilometers already shaking. While examining the seismicity around the June rupture, the researchers tracking this fault noticed something they could not identify. There is a distinct band of earthquakes between the Maacama and the Bartlett Springs faults. It shows up clearly in the catalog, a linear concentration of events, the signature of an active structure. But it does not appear as a fault trace in the National Quaternary Fault and Fold database, which is the authoritative United States inventory of faults considered active. The California Geological Survey's mapping shows structures in that area, but marks them as pre-quaternary, that is, not currently active. 2 working seismologists publicly asked for help identifying it. A reader pointed them toward a 2013 paper in the journal Geology, and a third seismologist independently pointed to the same paper. Sit with what that means. There's a prominent, seismically active structure in the northern California coast ranges that is not fully accounted for in the National Active Fault Database. Not hidden, not suppressed. The earthquakes are right there in the public catalog, just unassigned. And the Maacama's own history is longer than its catalog. Careful excavation of sediments near Willits identified fault offsets pointing to several large earthquakes on this fault within the last 1,200 years. That study deliberately assigned no magnitudes, because converting a single location offset measurement into a magnitude is not defensible science. But the researchers who reviewed the record, flagging clearly that they were estimating informally, put the likely size at magnitude 6.5 to 7 or larger, on the reasoning that smaller earthquakes do not leave a preserved geological record at all. Now apply the energy scale, which is logarithmic at roughly 30 times per unit. A magnitude 6.6 releases about 30 times the energy of the June magnitude 5.6. A fault that creeps and still leaves ruptures that size in the sediment is a fault where creep is not sufficient. Follow the trend southeast from the current activity and it stops being an abstract problem. The mapped Rogers Creek Fault begins in the general area of this sequence and runs southeast through Santa Rosa toward the Bay Area. For decades, there was an open question about what happened to it when it reached San Pablo Bay. In 2016, subsurface imaging led by the survey and published in Science Advances answered it. The Hayward and Rogers Creek faults are directly connected beneath the bay, with the Hayward bending about 10 degrees to the right as it crosses. They are one continuous structure. Combined length, roughly 190 kilometers, 118 miles. The maximum modeled magnitude for a rupture along that full combined length is 7.4. That number needs an immediate qualifier, and the survey is explicit about it. Multi-fault ruptures are real, but considerably rarer than single-fault ruptures. The joint magnitude 7.4 scenario is less likely than the individual Hayward scenarios, which model at magnitude 6.8 and magnitude 7.0. And those are already among the most consequential earthquake scenarios in the United States, because the Hayward runs directly beneath the East Bay. A magnitude 7.4 would release roughly 700 times the energy of the June earthquake near Ukiah. To be completely clear about what is and is not being claimed here, a magnitude 4.3 near Cloverdale does not load the Hayward fault. There's no mechanism by which it does. The connection matters structurally, not causally. The sequence is happening on the northern end of a fault system that runs continuously into the most densely populated corridor in Northern California, on a segment whose paleoseismic record runs 2 magnitude units larger than anything in its modern catalog. One more thing needs clearing up before we leave California. There is a second cluster of earthquakes in the same map view near Clear Lake and the Geysers, the largest electricity-producing geothermal field in the world, and it is a different phenomenon. Steam withdrawal and fluid injection remove mass and heat, the reservoir rock contracts, and contraction produces small earthquakes. That induced seismicity is real and openly acknowledged, but it is confined to the reservoir volume, shallow, small, spatially bounded. The Cloverdale sequence is on the Maacama structure, and the June rupture was more than 55 kilometers northwest of it. Clear Lake itself is a volcanic field that has not erupted in several millennia and is showing no eruption signals. 2 different processes, one map view. Now for the reason none of this made the news. Roughly 27 hours before the ground moved near Cloverdale at 4:30 in the afternoon Japan time on Tuesday, a shallow crustal earthquake ruptured beneath Kumamoto Prefecture on the island of Kyushu. The Japan Meteorological Agency put it at magnitude 7.1. The survey revised it to a moment magnitude of 6.8. The depth was about 10 kilometers, and it happened inland, not on the offshore subduction interface. It recorded Shindo 7 at Ukiah City and Hikawa Town. Shindo 7 is the maximum value the Japanese seismic intensity scale can express. There's no level 8. That scale has been maxed out only a handful of times in its history, and this was the first instance since the Noto Peninsula earthquake in January of 2024. A tsunami advisory went out within about 2 minutes for the Ariake and Yatsushiro seas, forecasting waves up to 1 meter, and was lifted about 2 hours later. There was no destructive tsunami and no threat to the west coast. The damage on land was severe. At least one confirmed death as of Tuesday evening. A person pulled from a collapsed house who later died in hospital. 20 to 30 employees were unaccounted for at a shopping mall in Kumamoto City, where part of the second floor collapsed, and then, roughly an hour later, an explosion tore through the complex, blowing out walls and exposing the steel frame. Witnesses reported smelling gas. The cause remains officially undetermined. That mall had reopened 6 weeks earlier, after being rebuilt following the 2016 earthquake. One hospital reported more than 50 wounded, another about 40, including 10 in serious condition. Approximately 300,000 people were directed to evacuation centers. Fires burned in Kumamoto City. Sections of the Kyushu Expressway split apart. Part of the wall surrounding Kumamoto Castle collapsed. Shaking was felt in South Korea. That is where the cameras were, and correctly so. That is where the damage was. Japan also supplies the case study that makes the California sequence worth taking seriously, and it comes from the exact same fault system. On April 14th, 2016, a magnitude 6.5 struck the Futagawa and Hinagu fault zones beneath Kumamoto. It was treated as the main event. Emergency response mobilized. People went back into damaged buildings. 28 hours later, a magnitude 7.3 struck the same system. The first earthquake was reclassified as a foreshock only after the second one arrived. Both produced Shindo 7. This is the reason the survey's word choice on the Cloverdale event carries weight. He called that magnitude 4.3 the potential mainshock of a sequence. That word, potential, carries the entire unresolved uncertainty of the discipline. There is no physical property that distinguishes a foreshock from a mainshock at the moment it occurs. None. The classification is available only in hindsight. The base rates are well established and reassuring, up to a point. Following any given earthquake, roughly 6% of the time a larger event follows within 3 days, and about 5% within a week. 19 times out of 20, nothing bigger comes, and that probability does not vary much across the magnitude 3 to 5 range. So a magnitude 4.3 is about 95% likely to be the largest event of its own sequence. The reason to pay attention is not that it probably is not. It is that the 5% case cannot be identified in advance, by anyone with any instrument. In 2016, it was identified 28 hours late. In 2011, the magnitude 9.0 off Tohoku was preceded by a magnitude 7.3 that nobody flagged as a foreshock either. Japan's own agency is applying that lesson right now. It has warned that strong aftershocks remain possible for a week, with the highest risk in the 2 to 3 days after Tuesday's rupture, a window that closes around today and tomorrow. The Prime Minister publicly told residents in the worst hit areas to prepare for another earthquake of similar scale. That sounds like inside knowledge. It is not. It is formalized protocol. And that protocol exists in this form because of 2016. More than 60 aftershocks had been recorded by Tuesday evening. The largest was a magnitude 6.1, almost exactly what standard aftershock statistics predict for magnitude 7.1 mainshock. The two largest early aftershocks sit roughly 35 kilometers south-southwest of the mainshock, along the Hinagu trend. There is a third reading from the same 48 hours, and it comes from the fastest converging plate boundary on Earth. Over the day and a half before this compile, the Tonga-Kermadec subduction zone produced a pronounced, spatially extended uptick in magnitude 4 and magnitude 5 events, on the order of 30-plus earthquakes across roughly 2 days. There were clusters to the north and to the south, with events at intermediate depths in between. A magnitude 5.1 struck south of Tonga at 10 kilometers depth. Tonga-Kermadec produces magnitude 4s and 5s routinely. Convergence there runs up to roughly 24 centimeters a year, faster than anywhere else on the planet. What is not routine is a dense, simultaneous depth-mixed cluster, shallow and intermediate events firing together in the same stretch of subduction zone. But the genuinely interesting observation is not where the earthquakes are. It is where they are not. A segment of the subduction interface, bracketed on both sides by those active clusters, shows essentially no earthquakes at all. Not in the last 7 days, not in the last 30 days. And that gap sits precisely where the interface begins, where strain accumulates. A quiet segment can mean two completely different things, and distinguishing between them is one of the genuinely unresolved problems in seismology. It can be an aseismic gap, where the fault slides smoothly and produces nothing because there is nothing to produce. Or it can be a locked gap, where the interface is welded shut and loading silently until it isn't. That same ambiguity is what makes the California picture hard to read. The San Andreas offshore of Northern California shows almost no cataloged seismicity, and it ruptured in 1906 at magnitude 7.9. The absence of signal in a system known to be loading is not evidence of safety, which raises the obvious question. 3 plate boundary readings moved inside 48 hours. Did one cause the others? No, and the reasons are more interesting than a yes would have been. Earthquake triggering works 2 ways. Static triggering is permanent stress change in the crust around a rupture. Powerful, well documented, and falling off so fast with distance that it is practically confined to within 1 or 2 rupture lengths. A rupture a few tens of kilometers long cannot load a fault 8,000 kilometers away. That stress change is not small, it is effectively non-existent. Dynamic triggering works through the passing waves themselves, and that one genuinely does operate at global distances. It was documented most famously after the 1992 Landers earthquake, which produced measurable remote seismicity increases, including at the geysers. But it has a consistent signature, strongest in geothermal and volcanic areas with pressurized fluids, showing up during or within minutes to hours of the waves passing, and overwhelmingly producing small events in places already critically stressed. Cloverdale ruptured about 12 hours after the Kumamoto surface waves swept past, well outside the window in which dynamic triggering is normally identifiable, and it happened on a strike-slip crustal fault, not inside the geothermal reservoir, where that sensitivity is highest. The defensible statement is that there is no demonstrable trigger relationship. These events are independent. That independence is the whole point, and it is not the comforting version of this story. If Japan did not push California, then California moved on its own schedule, from strain accumulated locally at 9 millimeters a year, on a fault that produced its largest recorded earthquake 5 weeks earlier, next to a structure nobody has formally mapped. The West Coast reading is a local reading. It is telling us about the Maacama's own state and nothing about Kyushu. Japan, Tonga, and Northern California are 3 separate gauges on the same machine. The Pacific Plate boundary is one system in the sense that it is driven by one set of forces and loading everywhere, always. It is not one system in the sense that one segment sets off another across an ocean. Approximately 62 earthquakes above magnitude 4 occurred worldwide on Tuesday, along with 14 above magnitude 5. That is a busy day. It is not an extraordinary one. Plot events at that rate on a globe and clusters appear by necessity, not by cause. So here is what to actually watch. And it is not the next magnitude number. The diagnostic is the shape of the aftershock distribution, and it applies identically in Sonoma County and in Kumamoto. If aftershocks stay tightly clustered around the mainshock hypocenter, that is a normal sequence decaying and releasing local stress. If they elongate along the fault trend, northwest toward Ukiah and the June rupture, or southeast toward the Rogers Creek fault, that indicates stress transferring onto adjacent segments, and segment-to-segment progression is exactly how a moderate sequence becomes a larger one. In Japan, the same test runs along the Hinagu trend, where the largest early aftershocks already sit. The survey's forecast gives a concrete checkpoint, at least one magnitude 3 or greater in the Cloverdale sequence within a week of Tuesday. Where that event lands matters far more than the fact that it happens. For Japan, the agency's high-risk window closes around today and tomorrow. If it closes without a comparable magnitude event, the 2016 pattern will not have repeated. One more thing rules out what people will otherwise assume. Tectonic tremor along the southern Cascadia subduction zone was checked Tuesday evening and returned 0, after running 307 epicenters margin-wide on July 14th and 382 beneath the southern margin on July 24th. Cascadia is not responding to any of this. What changed this week is not the loading. The loading never stops. What changed is that 3 gauges moved at once, and only one of them was reported. And the one nobody looked at is attached to a fault that has now moved twice in 5 weeks, that stores more than its creep rate suggests, and that runs straight into the Bay Area. The next 7 days of that aftershock map will tell us which kind of sequence this was. We will be tracking it.